Hello, hello, hello. Time for some chemistry. Hello. Let's get on with some chemistry. That's not good. I don't know how long that's been going on for, but it appears my microphone was out. Now, I don't know how long my mic's been out for. Hopefully not too long, because otherwise I've just been talking constant air to you guys, and I'll have to voice over that later on. So I'm gonna have to redo this lesson if it's that pants. So the first shell only has the S subshell, but the second has S and P subshell, and the third has SPD subshells. So let's get into it and what these all look like and what they all do. So here you can see I've got my sodium atom and I've drawn the electrons in different colors. There's a reason for that. You won't ever have to do that in your exams. You won't be expected to be pulling out colors. This is just to visually make it a little bit easier to see. So when we look at the first ring around the nucleus of sodium, we can see I've got 2 blue electrons there. Well, we say that they are in level 1, or the principal quantum number is 1, the energy level, and we use arrows for electrons, and there are 2 electrons in that subshell, and this is how we draw them, with an arrow up and an arrow down. I'll come on to that later, why we do an arrow up and an arrow down. Those represent a pair of electrons, okay? Now we go to the second energy level. Now, do you remember I said that they didn't all have the same energy, and this was carried out with some experiments, and they found that, hey, all these guys don't have the same energy. So all of these red electrons that I've done here in red, they're not really different colors, remember, but they all have, these pairs of electrons don't all have the same energy. The reason is when you get to the second energy level, we start with the 2s. 2 is the quantum number, and S is the subshell within that shell. So we've got the S subshell, but there's another subshell added when we get to the second level, and this is called the P subshell. And the P subshell can hold up to 6 electrons. The S subshell can only hold 2. And so I can fill this in, and really it's actually good to get in a habit to fill them in 1 electron at a time in each subshell. I'll come on to why that is a bit later, but it's a good habit to get in. So when we reach that second energy level, there are 2 subshells, the 2s and the 2p. When we get to the third ring, there's 3 subshells, 3s, 3p, and 3d. But we don't need to draw all of those because sodium only has 11 electrons. So sodium has the chemical structure, or the electronic structure, sorry, 1s2, 2s2, 2p6, 3s1. And we would write this in chemical notation because you wouldn't want to have to draw all these boxes at different heights. What do the heights mean? The heights give you an indication of the amount of energy. So we can see that the 3s subshell is a higher energy further from the nucleus than the 1s. Now, if I want to write this in subshell notation, I write this like this: 1s2, 2s2, and then I'm going to write 2p6. The p subshells can always hold up to 6 electrons with 2 in each box, and I'll talk about what these boxes represent in a second. And then 3s1. So now for sodium, in A level, when they ask you for the electronic structure of sodium, they want you to write that: 1s2, 2s2, 2p6, 3s1. You're no longer allowed to just write 2, 8, 1. It doesn't give you the full picture, this old model. It doesn't show you that actually in the second energy level, that those 8 electrons are at different distances and different energy levels from the nucleus. And this model shows that. Now, just to expand a little bit into this, what do these boxes represent? Well, they represent things called orbitals, okay? So in the S subshell, there's 1 orbital, and an orbital can hold 2 electrons. And S orbitals, they are spheres, circles like that around the nucleus. So if this is my nucleus of sodium, this black circle that I am showing here, then the S electrons occupy a sphere around the nucleus. That means at any 1 second or any 1 moment in time, those electrons can be expected to be found somewhere within that sphere. Now, p electrons are p orbitals, sorry, are slightly different. A p orbital looks like a dumbbell, like this. And at p orbital, it means at any 1 second, say I go to 2p here where I've got 2 green arrows, I'm just moving my red cursor over it now. It means at any one moment in time, those electrons could be anywhere within this configuration, which looks like the number 8, or a dumbbell, people often describe it as. And this black circle is my nucleus. So if the nucleus is there, we can expect to find those electrons at any one time somewhere around the nucleus in this configuration. Okay, so it's kind of a mathematical probability of where they'll be at any one time. Now, can actually draw a line just so you can see the plane of this. Now you notice that there are, that's called a p orbital, this one I've just drawn that looks like a dumbbell, and there's 3 of them in the p subshell. There's 3 orbitals in a p subshell. So orbitals are smaller than subshells, and that is the worst dumbbell I've ever seen. There is another, or one of the p orbitals, going like this. Now at AQA, when you're doing this, you don't need to know about the structure of orbitals, but it's worth doing, although I have to say that's possibly the worst orbital that has been drawn in the history of orbital drawings. So we've got a dumbbell horizontal in a plane like that at right angles, the second p orbital. So it means that this second set of electrons that you find here in the second box there in sodium, the green arrow up and the green arrow down, they will be found anywhere. Imagine this black circle in the middle is the nucleus. Those 2 electrons will be found anywhere, buzzing around like flies in your kitchen, in a figure of 8 somewhere in there. And that's all been proven mathematically with very complex equations, far beyond my brain power. And then there is another dumbbell, getting a bit funky now, coming diagonally through. So if you've got one like that, you've then got a third set of dumbbells going diagonally through into the paper like this. And we can name these, I don't know, you can name these X if you want, Y and Z, and these orbitals. So at AQA, you don't need to enable these X, Y, and Z, but it's just cool for your own knowledge to know that you have these orbitals, and the p orbitals have a different shape than the s orbitals, but they're not a structure. There's no membrane or wall around them. There's no physical structure holding them in. This is just a mathematical possibility of where those electrons are around the nucleus at any one time. Okay. And p orbitals are at a higher energy level than the s orbitals in the same subshell. So there we go. New information for A level. Your old shells, your old energy levels, the rings around the atom or around the nucleus within an atom, those rings or energy levels are divided into subshells, S, P, D, and F, and those subshells are divided into orbitals, these little boxes I've drawn here. And each orbital can hold maximum 2 electrons. But as you can see, it doesn't have to have 2 electrons. If there aren't enough to fill one, as we can see with the 3s orbital over here, it'll only hold 1. Now, on to why we draw an arrow up and an arrow down to represent the electrons. So if I circle this box here, you will see I've drawn an arrow up and then an arrow down when I put the second electron in. And well, there was a guy called Pauli with his exclusion principle, and he came up with, his theory is that the electrons spin in opposite directions, and this minimizes the repulsion between them. So one of the electrons in the s orbital, in the sphere, is spinning that way, and the other electron is spinning the other way. And this means if they come close to each other at any time in their movement, the repelling factor, because they both have 2 negative charges, is minimized by the fact that they're spinning in opposite directions. So spin pair repulsion theory. So that explains why they spin in opposite directions. Now, moving swiftly on, we're going to look at another atom now, because calcium in our periodic table has 20 electrons. So this gives me the chance to show you some of the an atom with more electrons and how we break down the subshells. So let's go. Right, if I've got 20 electrons back in old GCSE money, and I need to move my camera, so let me just move my camera because my fat head is in the way. Right, there we go. Back to the screen. Boom. Right, 2, 8, 8, 2. So microphone problems early on there, which I'm going to go back and correct at the start of the video, but what are we going to do? Yeah, so in old money, calcium would have been 282, 2882. And why would it be that? That's because calcium has the atomic number of 20, which means it has 20 electrons around the nucleus. Okay, but we're going into our atomic model with more information. So let's whack our electrons on. And we can put our electrons on, one there and one there. So our electronic structure for calcium, we've got 1s2, then we hit the second ring further out from the nucleus. This energy level is slightly bigger, and it's kind of nice model our old GCSE one because the rings get bigger, don't they, as we go away from the nucleus. So we can whack in 2s2, but now in the same ring or the same energy level, we have a 2p subshell, and the 2p subshell is made up of 3 orbitals, these boxes, and each one can hold 2 electrons. Notice I filled them one at a time like this. Whenever I go into a new subshell, I will fill them one at a time, and it's a really good habit to get into, which I'll explain why later. So it's actually the way that we should fill the electrons in the orbitals, and I'll come on to that later in a minute. So we've got, okay, let's whack through these. You can see it's all going quite well. I've done 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I'm going to go 13, 14, 15. Notice here, I've now added 16, 17, 18 of the 20 electrons. Notice we've got a new orbital structure coming in the third level. Remember what I said, with each level it goes 1s. The first ring over here in calcium just has 2 electrons, so it just has an s orbital, a sphere, as its subshell. Then in the second energy level, there are 2 subshells, an S and a P. The S subshell is a sphere made of 2 electrons in its orbital, and then the 2p subshell is made of 3 orbitals, X, Y, and Z, but you don't need to call those X, Y, and Z at A level. And then we go to the third energy level, which is the third ring around the outside of calcium. We find there are 3 subshells, 3s, 3p, and 3d. So we've had a new one added. And if calcium went through all of the 4th energy level of electrons, then we'd have 4s, 4p, 4d, and 4f. Okay, coolio. So got something that's a little out of the ordinary here, and this is where it starts to get a little bit complicated. So far it's all been quite nice. Normally we just go up in the levels in that order, but when we come to the 4s energy level, you can see there is an anomaly here. Okay, there is something slightly different. Normally the 3s energy level is going to be lower than the subshells above it, or the 4s, sorry, or the s subshell is lower. But when we get to the 4s, we find that the 4s subshell is lower in energy than the 3d subshell, which is a bit odd. So it's kind of like you're imagining the 4th ring, 1, 2, 3, 4, dipping in at a point. So if I was to get rid of, where is that? Right. So if I was to draw this is the 4th energy level, which is 4s, 4p, 4d, and 4f. It's like it dips in here at a bit. So 2 of the electrons it carries are at a lower energy than the 3rd ring. So that's what happens. And what we do, you just have to remember that the 4s fills up before the 3D. So actually calcium has no electrons in the 3D, it fills the 4s first, and that's for all atoms. So note the 4s orbital fills up before the 3D subshell. Now you might be getting confused between orbitals and subshells, so I will remind you of the difference. So, quick reminder, an orbital can hold 2 electrons and is represented here by any one of these boxes. A subshell are the smaller shells within an energy level. So in shell 1, there's only one subshell. In shell 2, there's 2 subshells, which is 2p and 2s. In shell 3, there are 3 subshells, hence the number 3. There's 3s, 3p, 3d, and in 4 subshells, in the 4th energy level, there are 4 subshells, S, P, D, and F. Cool. Right. Super. So that's the electronic structure of calcium. Now, what we do need to know is the that you will never really be asked. You may get a diagram with these boxes in certain syllabuses and certain A levels that you've got to fill in. This is more for your understanding of where they're at in terms of their energy, this diagram. It's often not tested in exams. What you will be asked is something like, give the full electronic structure for calcium. Okay, and the subshell notation or electronic structure for calcium is as follows. So for calcium, it is 1s2, 2s2. Now this doesn't give you as much information because you write 2p6, and so you can't see that there's 2 in each of the 3 orbitals, but you can imagine that. 3s2, and then 3p6, and now it gets a bit weird. We're supposed to go to the 3D, but instead we go 4s2, and the 3D is actually after the 4s. So a little bit weird. We dip into level 4, so that's why A level's tricky. Right, need to move my fat head. Gonna be moved. Just about squeeze that in there. All right, awesome. Okay, there we go. So there is the electronic configuration for calcium. It's going to be a short lesson today, so probably should only be an hour. Make sure if you are watching this on a rerun, you hit the like, you subscribe to the channel. I'm doing my biology Tuesday at 8 p.m. These are free tuition lessons. You can come on and interact live. You can ask me questions. When term starts, if you're stuck with homework, you can ask me questions about your homework. At the end of the lesson, I'll stick about and help people with any problems they've got, any stuff they're struggling with biology or chemistry A levels. So yeah, make sure you subscribe and you get involved. All right, subshell notation. So we just saw calciums. Going through calcium again, 1s2, 2s2, 3s2. Oh, I think I'm dying a bit here. It's writing out all these subshells is a bit of a pain in the bum, isn't it? Really. So yeah.
You better move on, or else.
Yeah. So anyway, let's get back to it before that guy with a bat beats me up. So we go 1s2, 2s2, 3s2. No, that's certainly not right. That's what happens when you rush. So what happens? 1s2, 2s2. What comes after the S when we get to the second level? It's the 2p subshell, and it's 2p6. Then we go to the third level and we start with S, and there's 2 electrons in that. And then we have P, 3p, and there's 6 electrons in that. Now we're in the third energy level. We're going to add a third letter, a third subshell, and it's the 3D. However, it's controversial here. You could write 3D if you wanted, but there'd be 0 electrons in the 3D. And then there would be the 4s. Now, weirdly, the 4s, this is the anomaly in chemistry, the 4s fills in Chemistry A level anyway. The 4s fills before the 3D. So I'm going to get rid of my 3D, and I'm going to rewrite that by putting my 4s straight after the 3p. So 3p6, 4s 2. And that should add up 2, 4, 10, 12, 18, 20. There's calcium's electronic notation. So some people like to put the 3D after the 4s. Some people put the 3D beforehand but don't fill it out. It's probably easier to put the 4s before the 3D, as that's the way it fills. But when you empty, this is where it gets really complicated. When you go through and lose electrons, when you're becoming a positive ion, you actually lose electrons from the 4s first. So it gets a bit confusing which way you should do it. I prefer to write the 3D then the 4s, but then you have to remember to fill the 4s first. So either way you do it, you've got to remember there's a trap there. Right, noble gas shorthand. That took absolutely ages, me writing that out. So there's a shorthand way for us to do this. If we look at the closest noble gas to calcium, and if I go here to my wonderful periodic table that I've colored in very badly, we can see calcium is here, and calcium has 20 electrons. So what's the closest noble gas that's below calcium in the number of electrons? So I need to go back here to the noble gases. I've got helium, I've got neon, argon. If you look, argon has 18 electrons. Now, because argon is a noble gas, it's going to have a full subshell and a full energy level. And that means I can do a shorthand and then just tag on the extra electrons, and it saves me writing all of those out. Sometimes in exams they say they want the full electronic configuration. Then you do it the way I've just done it. But if they don't, then we're going to use the shorthand. And here we go with the shorthand. So as argon, I can actually say that, so here's calcium's full subshell notation. But if I want to cheat and do the shorthand, I put brackets, I write the symbol for argon, AR. Now, argon has 18 electrons, so it's going to be equivalent to saying 1s2, 2s2, 2p6. That's 10. That's actually neon's electronic configuration. Now we add 3s2 and 3p6. So actually, argon has this electronic configuration. So I can just write AR instead of writing all of that out. What a lifesaver. Which is really great because nobody wants to spend their life writing out 1s, 2s, 3s. So round of applause for the shorthand. Okay, right, back to business. So I'm just left with the 4s2. So check this out. That there is the shorthand for calcium. I can just write calcium calcium is argon. I don't really need that little black dot there. Calcium is just argon with 2 extra electrons, and that's the shorthand way of writing the electronic configuration or structure for calcium. So I hope that helps. So we're just about halfway through the lesson. So let's crack on and smash through the rest of the lesson. So there are two, transition metals behave unusually. You're going to do a lot on the electronic structure of the transition metals and why they behave unusually. It's to do with the 3D subshell. But we'll look at that a bit later. But what I'm going to do is pick these two anomalies, two exceptions. Now, most of your chemistry A level, especially your inorganic chemistry, is going to be learning trends and patterns, memorizing the trend and pattern, i.e. how we write all these electrons out, and then learning that there are some exceptions that break the rules. And then you need to be able to explain why they break the rules and how this helps us. And so, you're going to be really quizzed on the ones that break the rules in the harder questions. So these ones kind of break the rules slightly, but they're not really breaking the rules. They're just not as we would first appear. So if we look at chromium, chromium has 24 electrons, and I'm going to just show you chromium over here. So chromium in my blurred out periodic table is there. As you probably can't see that because I got a bit excited with my highlighter pen. It has 24 electrons. This means if I want to do the shorthand, the closest thing to it is argon. So I'm just going to do the shorthand for argon. What we would expect it to look like would be like this. Chromium, shorthand argon, which is 18 electrons, and that leaves me with 6. Did you remember argon, that the final subshell that's filled in argon is the 3p6? So I've now got 4s2. So I would expect it, if you remember I said it fills the 4s2 first, and then there's 4 more electrons, and we've got the 3d subshell. Now I haven't told you about the 3d subshell. The d subshell can actually hold 10 electrons. That's right, it's made of 5 orbitals. And if I was using the boxes for these orbitals, I'd be saying, let me just duplicate this box. Bit long, I've got to duplicate that 5 times. Get on with it, Tom. Okay, bear with me, bear with me. Right, so kind of going over into my copper information here. I'll just delete this and do copper separately. So why am I writing boxes underneath? You wouldn't normally do this, but this is to help explain what's going on with the electrons. So we would expect the 4s orbital to fill first, like this, and then we'd expect the remaining 4 electrons, because argon is equal to 18 electrons, so then the 4s2 and the 3d4, that makes 24. We'd expect it to fill like this. But actually, this is not what it does. So this is how we would expect it to fill. It would go 4s, 3d. However, there's a slight difference. What it does, chromium, instead, what we actually find that chromium does, don't ask me why I put the R up in the air there, it's having a little fly. Chromium moves one of the electrons from the 4s into the 3d. So we end up with 4s1, 3d5, and it's going to look a little bit like this. So we've got the 4s1, bit painful this, kind of wish I'd done this earlier, but never mind. You can always fast forward through it, it's not that bad. Let's go. So okay, let's smash this out. Right, actually it does this. So it takes 1 electron from the 4s and jams it over here. And why that's better for it is when you put 2 electrons together, there is a little bit of repulsion. So it's more stable for the argon to say, listen, I'll take one of those 4s electrons, which is spinning oppositely, but still getting repelled, and I'll sling that in that empty orbital in the 3D subshell. Now, having empty orbitals like this in a 3D subshell, if they can help it, an atom does not want an empty orbital. It makes the subshell unstable. It's much better to have these 2 half-filled subshells than the 4s completely filled and the 3D partially filled. So what we learn from this is that half-filled subshells are more stable electronically, energetically, than partially filled subshells. So there's an important note to make there, and that's a rule which you'll need to know, because when you're writing this out, if you have the opportunity to make a subshell half filled, and it will be the final one you're filling in, because the others will be completely full before that, then you would need to make sure that it's half filled rather than partially filled. So there's an exception. They may give you a multiple choice question, and you'd have various different electronic structures of chromium, and you'd need to be able to spot that chromium is going to prefer to be like that. Let's check out copper's issue and what copper is getting into. So what I'm going to do now, I'm just going to rub this out, and we're going to have a look at copper. So I just have to make a few minor adjustments. Copper is just swap the Cu. And argon is the closest noble gas to copper, right? So we're going to stick with argon, but yeah, argon's the closest noble gas to copper. So we've got to add, we can do 29 minus 18, and that leaves us with 11. Incredible math skills. Yes, so it leaves us with 11. So what we're going to do now, I don't really need to rub out the old 4S or 3D notations. I just need to, actually, I just need to do this. Boom, 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 boom. Get rid of these electrons, Tom. We don't want to be, oh, no, we'll keep that. We'll stop deleting there. Sounds good. Oh my good gosh. It's taking a long time. So, see you. Sorry if I'm being a see you next Tuesday, but that's what you get. Okay, let's do this. Huh? Right, so we're looking at copper now, and copper has got 29 electrons, so its outer electrons are going to be in the 4s and the 3d. So we've got the same thing here. The first 18 are used up over here, and we're left with 11 electrons. So what we would expect, and then what actually happens is over here. So here is what actually happens. Okay, so let's go through what we'd expect. What I'm expecting is these 11 electrons to bust like this. 1, 2. My tea's getting cold. Funky periodic table teacup. Only £4,000. Send your payments down below. Yeah. Okay, how many electrons is that? 1, 2, 3, 4, 5, 6, 7. Glad you don't have to do this a lot. We're going to go through some exam questions in a minute, so stay tuned. 1, 2, 3, 4, 5, 6, 7, 8. Gosh, my adding up skills on the fly are not good here. So we're up to 8, 9, 10, 11. So we'd expect that situation, right? We'd expect copper to be 4s2, 3d9. Okay, so we're expecting 4s2, 3d9. And what do you think copper really does? It says, hold on, I can make myself a bit more energetically stable. What is this? So this is I'm going to right underneath this box, this is a full subshell. So the 4s is full. Is the 3d full? No. The answer is no. The 3d can hold 10 and it's only got 9. That counts as a partially filled subshell. Now, do you remember I said a half-filled subshell? The rule is that a half-filled subshell is more energetically stable than a partially filled. Is there a way we can make this a full subshell and a half-filled instead of a full and a partial? Well, there is. What can happen here is this electron can be shifted over here and create a full 3D and a half-filled 4s. Half and a full is more stable than a full and a partial. So I'll draw these ones in blue. I don't know why. I like using colors. Okay, so and he's already gone and whacked that one in. So instead of putting that electron there, it's always good to fill up as we mean to go on. Right, you go like this. Now, the reason I said earlier, fill them up one at a time like that when you're doing each subshell is because then you can kind of work out what's the most, it kind of helps you see what's the most stable configuration. And this is the most stable way for those last 11 electrons after the argon structure to go in for copper. And that is that we end up with a half filled subshell, and we end up with a full subshell. And that configuration is much better than the one above, the full and the partial. Full and partial, not as good as a full and a half. So they're able to move their electrons about, and what we're really looking at is copper and chromium. We don't fill up in the way we would expect. So because of that, there's a little exception there for you to get into and to learn. All right, guys, I hope that was helpful. What I'm going to do now, I'm going to move into oh, nice, Mohammed. You're doing maths, physics, and chemistry. Awesome. Yeah, that's very mathsy. Maths, physics, and chem. I'm doing chem every single Monday. I've done I did one last lesson, and I'm doing last lesson. I did one last Monday at 8. I'm going to be doing them every single Monday. When you start in September and you're getting stuck on some of the chemistry homeworks or worksheets or whatever, you can just come on at the end of my lessons from September. I'm gonna oh, thanks, Zainab. I'm gonna at the end of my lessons I'm gonna do what do you call it, like where I help people when they're stuck with certain questions. Yeah, further maths, physics, and chem. You guys are heroes. You deserve an applause. Yeah. I'm going to be going live. I'm going to be going live when school starts in September. Yeah. So I'm going to be, yeah, defo going live then. So this is a periodic table at A level, although I have colored it in really badly. You might be wondering, I mean, really, I want to get rid. Oh, sugar. What did I do there? I don't even know what I did there. Yeah. Okay. So yeah. So Monday's going to be chem. Tuesday's going to be biology. So I'm just doing a lesson every week just to kind of. It's really just about practicing myself with the lessons. So by the time you guys start in September, I'll be a little bit ahead, but you can always rewatch the old lessons. And then obviously people will be getting different homeworks and getting stuck on things. So I'll kind of do like a help thing at the end of each lesson as well. You notice I've colored in the periodic table in different colors here. We call this the S block. This is known as the D block, and this is known as the P block. And the outer electrons for these atoms always end in an S orbital, which if you watch earlier in the video, I've been talking about that. Although I think my mic wasn't on for the first 5 minutes, which is embarrassing. So I'm going to go back and have to voice over that bit. And then anything that is finished in this yellow section of the periodic table is known as the D block. Its outer electrons, its last couple of electrons, are in the D subshell. And then if you're in this section, one of the non-metals or some of the metals there, then your outer electrons are in the P block. So they're in a P subshell, like 2P, 3P, etc. Yeah, you guys can press save on the video, by the way. This video will be available for you to watch whenever you want, and you can save and download. You can download the videos or save them. That's all available to do on YouTube as well. Like underneath the video, it says how, like once it's there, it will be about, so you can save it. The last week's one was on something called time of flight spectrometry, and you'll find that one there as well. So that's a way of us calculating the relative atomic mass. And I went through some exam questions. So If you haven't been watching today, then you might find, yeah, it's a big jump from year 11 to year 12. It's a big jump from year 11 to year 12. It's the biggest jump in education, actually, GCSE to A level. It's definitely the biggest jump that you get anywhere in your education. The jump from A level to university is nowhere near as big. Like, the concepts at uni are not that much harder than, in fact, a lot of your A level content will appear in a lot of your uni content. So the jump to uni is nowhere near as big as the one from GCSE to A level. Yeah. You might recognize this. This is the atomic structure J.J. Thomson. He discovered the electron and he came up with his plum pudding model. And his model here, he's just got these electrons inside an atom here. What are two differences between the plum pudding and today's current atomic structure? So that's almost a GCSE question. You guys will have done that at GCSE. So any ideas? What would be the difference between the plum pudding and the actual atomic model we use today? Okay, slurping my tea away. Yeah, plum pudding has the electrons embedded. Where are the electrons found, Zainab? Where are they found in the modern model? Yeah, today they're in shells. Great. So yeah, electrons. Whoa, I can't even do the electron shorthand. Electrons found in shells, and then in today's lesson, which you guys might not have been here for the full lesson, there's yeah. You're right. We've got subshells as well. And we've got things called orbitals. So electrons are actually found in energy levels or shells. And then within each ring, each energy level, there are subshells, which I was talking about earlier in the video, SP and D. So not all the electrons in the same ring on the old GCSE model of an atom are of the same energy. They're actually broken up, those rings, into different subshells, different distances from the nucleus. So yeah, and that would get you 2 marks. Yeah, it has a positively charged. Yeah, there's a positive nucleus. Yeah, great. Yeah, those are all really good points. You'd smash that one out the park. Now it says deduce the full electronic configuration of an atom of R. So in old money, we would count here how many electrons are here. And you might remember from your GCSE structure, we could work out what would be the electronic structure in old GCSE method of that atom. Any ideas what the electronic structure would be? And I don't know if you can see that, but there's 7 electrons. So what would the electronic structure be in the old GCSE method? Just taking a sip of my tea, keeping myself. Yeah, well, these 7 electrons, it would actually be 2, then 5. So the electronic structure would be 2, 5, because we would put them into rings. Now, it does tell us what group they're in, that the new electronic structure, but this asks, and if you weren't watching the video earlier, you find this a little bit tricky. That's right, Zainab, 2-5. If you weren't watching the video earlier, you'll find this a bit tricky. But the full electronic configuration of an atom of element R, we actually break the first energy level is called energy level 1. So we write a 1. And then the electrons are found in an orbital called the s orbital. So we write 1s2. And then the 5 electrons that it has in the second ring. So on old GCSE method, we would do it like this. We put 2 there, and then we put 5 like this. But in the new A-level method, I say new, it's not new, but it's the method for, I was doing this 25, more than that, 27 years ago in my A-level, so it's not new by any standard. But you go in the second energy level, there's also an S subshell. We call it a subshell, a smaller shell within, and that is called the 2S subshell. And then in the S energy level, there are two levels. There's the 2p, so it'd be 2s2, 2p3. That would be the electronic configuration. So it'd be 2s, it'd be 1s2, 2s2, 2p3. And then it doesn't have enough electrons to enter the third energy level and the third ring. The third ring is made up of an s orbital, which can hold 2. P orbitals can hold 6. This one's only got 3. So if I zing back here, gone a little bit too far. Okay, so if I zing back here, this is my sodium atom I was covering earlier in the video. And the first ring, you can see with these blue electrons, the first 2 electrons of any atom go into what's called the energy level 1, principal quantum number 1, or the quantum shell 1, or quantum energy level 1. Those are ways to say the first ring, basically, or the first shell. There's 2 electrons in the first shell, and they're found in an s orbital, which is a sphere-like shape. But you don't need to worry about that if you're doing AQA. You just need to know that there's 2 electrons in an s subshell. I called it an orbital. This box is an orbital, but we call it a subshell. Then as we go to the second energy level, which is all of these 8 green electrons I've got here, we have a 2s, which is a subshell. So that means that these 2 electrons over here are at a slightly lower energy. They're slightly closer to the nucleus than the next 6 electrons, which are found in what we call a 2p subshell. So it's just giving you more detail. The old GCSE method didn't let us know that some of the electrons within the same ring are closer to the nucleus. We just draw them as a circle, but actually they're a little bit closer. And some are further from the nucleus. The P ones are further. The further you get from the nucleus, the higher energy. That's why the P is above the 2s. Then we jump to 3s. And then in the third energy level, I've got calcium here. In the third energy level, we go from 2p to 3s, then 3p. So the next 8 electrons is 2, then 6. Then there's a 3d energy level with 5 boxes or 5 orbitals in it, so possible 10 electrons. In fact, the third ring at GCSE, you were taught to go 2, 8, 8, 2, but actually the third ring can hold 18 electrons. So the third level can hold 18, 2 in a 2s, 6 in a 3p, and 10 in a 3d. But then there was an anomaly if you watch the video back, and that is that as you fill up the energy levels, what happens is 2 electrons go into the 4s first. So yeah, before the 3d, but you'll have to watch the video back to work out what the hell that's about. So so here when I'm filling this up, we have a new way of writing the electronic structure. And so there it is, 1s2, 2s2, 2p3. And then the next question says, identify and deduce the formula of the compound form when R reacts with a group 2 metal in the same period as R. So we're going, right, this element R, first of all, what is element R? Well, it's got 7 electrons. That should be easy enough. Yeah, Zainab, chemistry A level is definitely difficult conceptually, but once you get the hang of the patterns and the trends, you'll get there. If you haven't watched the start of the video, then you'd be confused, because at the start of the video I went through that whole system and explained it all a bit slower and in more detail. But it's definitely, you will find, what I would say with chemistry A level, you will leave lessons in the first year, you will leave many lessons confused and baffled. And if you're not comfortable you know, like it's, I don't know whether you had that with higher maths or with, if you did further maths, where you leave lessons, you're like, whoa, what was that all about? You are going to leave lessons like that. And I did an introduction video to chemistry and biology A level. Biology A level um, is, you're not going to leave lessons really that baffled. There'll be a few you leave baffled, but you're going to be overwhelmed with keywords and content. Um, whereas with chemistry A level, the concepts are difficult. But once you've cracked those concepts, sometimes it takes a little while to sink in. Once you've cracked it, you've got it. And it's therefore a lot less revision. I don't want to say a lot less. A levels are a lot of work. And in my recommendation, you do 5 hours a week per A level. So if you're doing 3 A levels, your school will give you 15 hours of A level lessons. If you do 4 A levels, if you're nuts, then you're going to do 20 hours of lessons. Now at GCSE, you did 25 hours of lessons. This means you have 10 hours free in the daytime in your college or school. Not all colleges or schools let the sixth form off site. If they do, you can go out, play pool, go to a shop and have a drink, meet up with friends, have a coffee, or you can go to the study room and study. But really, you're being treated more as an adult. You have to say, right, I'm doing 3 A levels, only 15 hours of teacher time. Those 10 hours are for me to do purely on my work. So if I choose to not, and you're an adult, so you're becoming an adult. So if you choose not to do that work in school in your study periods, you need to go home and do that work. If you do that, if you do 5 hours a week per A level outside of school, you can get an A or an A star. I've never met a student who did that. So you might want to do your hours on the weekend or 1 hour a night or whatever. Some people do 1 hour a night, but that's 3 hours after you get home from school. That's long, like with family commitments and things, that's quite long. But if you do that every day, you'll crack it. Yeah. Now the AS level, if you're just doing an AS in chemistry, Zainab, you're going to find any of the science AS levels, they're all going to be tough. Okay. Biology is going to be conceptually easier with lower grade boundaries, but you've got to get the exam technique down. The reason why the grade boundaries are lower is because more students flop at biology. In terms, don't flop because they allow the same amount of A's and the same amount of B's and the same amount of C's, but the students score less marks on biology, so they move the grade boundary, they move the bell curve back. But you are going to find that all AS levels are hard. You could do an AS level in music or drama, they're going to be incredibly hard. All A levels are hard. They're very well respected around the world as a true indication of talent, basically. So they're very, very hard work. And it proves if you get a good A level or even a D, even a C, B, or A, if you're in that region, that proves to an employer or a college this person knows how to work. You can't fluke it. There's no fluking at A level or squeezing by. So if I go back here and I've got 7 electrons, which atom in this periodic table has 7 electrons? You should be able to find which atom has 7 electrons. Yeah, Karam, this video was, if you watch it from the start, it was on S, P, D, F orbitals, subshells, and talking about orbitals. Didn't go in too much to wave function and probability, but absolutely the orbital shapes tell you the probability of where the electron is around a nucleus at any moment in time, and their different shapes, the different orbitals. That's right, it's nitrogen. So the atom is nitrogen. So that's going to look at how stingy they are at A level. This is a 1 mark question. They then say they also want you to write the formula of the compound formed when R reacts with a group 2 metal in the same period. Now you should remember that the same period, the period is the row on the periodic table. So nitrogen is in period 2. Hydrogen and helium are the lonely guys in period 1. Nitrogen is here in period 2. Which is the group 2 metal in period 2? What's the group 2 metal in period 2? You probably can't see on here. I've covered it in so much writing and graffiti. Yeah, so we've got beryllium. Now, so we know, going back here, nitrogen and beryllium are going to form a compound, and beryllium being a metal and nitrogen being a non-metal, you can tell me, is it going to be covalent or ionic? Do you remember from GCSE, if you've got metal and non-metal, is it going to be covalent or ionic? Yeah, it's going to be ionic. Now, we didn't really need to know that, but it's okay to know that. Then we always write the metal first, then the non-metal. Yeah, that's right, Zainab, ionic, metal and non-metal. What's the charge going to be on beryllium? When it becomes an ion, it's in group 2. Is it going to be +1, +2, or +3? How many electrons would it lose? Yeah, well done. 2+. Well done, guys. Both of you spot on. So it's going to be 2+. Now, nitrogen is in group 5. Is it easier to chuck away 5 electrons or take 3 electrons? It's much easier to get 3 electrons. So what's the charge going to be on nitrogen when it forms an ionic compound? Yeah, that's right. But nitrogen is going to steal 3 because nitrogen has 5 electrons in the outer shell. So nitrogen's going to steal 3 and become -3. Brilliant. Which means, and Karam's right there, Be3N2. How do we write the formula? Well, some people say swap and drop. So you see the 3 above nitrogen on the right hand side. You can swap that over and drop it down, so it's Be3. You can take the 2 that's above beryllium, swap it over to the nitrogen and drop it down, and you get the formula Be3N2. And that would be, what would that be called, that compound? By the way, that's just one way, swap and drop method. Personally, I don't use the swap and drop. I cancel out the charges. So I go like this. I go, right, I need to cancel them out. What can I multiply them by? I go, right, if I multiply nitrogen by 2, I get -6. And if I multiply beryllium by 3 times 2 plus, I get +6. And +6 and -6 cancel. So when I'm working out compounds, that's what I do. But some people do the swap and drop method. Yeah, you could do that method as well. Personally, I just kind of multiply them up and then. What do you think this is called? What's this compound called? It's made of beryllium and nitrogen. Do you remember what compounds end in? When you have 2 elements in a compound, what 3 letters do they end in? Think magnesium and oxygen. What would you call magnesium and oxygen? And then what would you call beryllium and nitrogen? Same kind of thing as magnesium and oxygen. Close. Nitrate, ATE, is when there's 3 elements. When there's only 2 elements, instead of nitrate, magnesium and oxygen become magnesium oxide, 2 elements. What would beryllium and nitrogen? Yeah, beryllium nitride. Beryllium nitride. Close there. Yeah, beryllium nitride. Yeah. So it hasn't asked for the name, but it'd be beryllium nitride. So if it was sodium and chlorine, sodium chloride. If it was sodium, chlorine, and oxygen, 3 elements, sodium chlorate. So let's look at a couple of these SPDF business. Right, so what you're looking at here, back in the old days, we said that the 5 electrons in the outer shell of nitrogen, it is in group 5 still, We haven't changed that. It's still in group 5. There's 5 electrons in the outer shell. We now just break that shell down into an s orbital and a p orbital. S can hold 2, p can hold 6. And so the more detailed understanding of those 5 electrons is 2s2, 2p3. Right, you'll have to watch the video to catch that. You probably won't be able to get these if you haven't watched the start of the video, but I'll take you through it. Which electronic configuration of an atom with only 2 unpaired electrons? So what I can do here, see these, the p orbitals look like this. So that there's 3 pairs of electrons in the p subshell. So 2p3 means I've got one here. We draw arrows, and we draw an arrow up and an arrow down. The electrons actually spin in opposite directions to reduce repulsion. So how many unpaired electrons are there? There's 3. I want one that has 2 single electrons only in the box. Yeah, arrows represent spin. That's right. So the arrow up. So if I look at this one, 3p5, I'm only drawing out the last one because it's like the only thing I'm interested in. So 3p5, this means it's in the 3rd ring, and p always has 3 boxes, 3 orbitals. Those orbitals are actually dumbbell shaped, but you don't need to worry about that. Now, 3p5, I've not made this very big. You draw an arrow up and an arrow down. The arrow up and down show that the electrons in the same region spinning in opposite directions. One is spinning this way and one is spinning that way. If they ever pass each other, it minimizes the repulsion between the 2 negative charges. So, yeah, you're right, Zainab, but you've got to be comfortable with being uncomfortable. It's nothing that your brain cannot grasp. You can definitely be on top of this. How many, Zainab, let me ask you a question here. How many of these boxes how many is there 1 electron in? So we'd say it's not in a pair. How many boxes have an unpaired electron? How many boxes here have an unpaired electron? Just the 3rd one. So that can't be the answer. And up here, you're absolutely right. And up here, all 3 have an unpaired electron. And it's asking me for one that has 2 unpaired electrons. So all you've got to do is draw out the boxes. All right, this one's a bit deep. Yeah, there's going to be multiple choice, by the way. You get a whole load of multiple choice questions. In fact, is it paper 3? You get 20 multiple choice questions. I'll have to check my introductory video. But the 3D level has 5 boxes, and it tells you that there's 5. When we're filling electrons, we always fill in the most stable way first. So you do 1 in each box first. This is the most stable configuration. They prefer to have them all half filled than just 2 like completely filled. They would rather have it all half filled. It makes it more balanced and stable. So this one is not the answer either. And then if I look at this one, that's why I saved it till last, 2p4. Again, what does the 4 mean? There's always 3 boxes, but there's 4 electrons. So if I go through and put the electrons in, 1, 2, 3, go back to the first orbital, 4, what you'll see here is there are 2 boxes that contain an unpaired electron. It's not in a pair. So the answer for this question was B. So yeah, you might say, how would I work that out in a minute? Obviously, you wouldn't draw all these boxes out once you become skilled, but this is the way to show you how you could do it. Once you become skilled, you'd look at the 2p and you go, right, 2p's got 3 boxes, 1, 2, 3. There's going to be 1 with 2 in and 2 with 1 in. Bang, it's B. So it would only take you a few seconds because you could do it in your head when you get to that level. Yeah, we're only looking at the last shell in this particular question because all of the levels before that will be paired up. 1s2, 2s2, 2p6. They're all filled up already, so they'll all be filled. So you're only looking at the last energy level on all of these. Yeah. And then this one says, which one has an incomplete subshell? The subshell are the letters, the subshells are the letters the letters S, P, and D. And in the first ring, you have an S. The second ring, you have an S and a P. The third ring, you have an S and a P and a D. So with each level, they add another subshell, like mini shell within a shell. Freaky, I know. Right, if we look at beryllium, we just got to look at the electrons. Beryllium on our periodic table has 4 electrons. So that means beryllium is 1s2. And then we go to the second energy level, which we write the number 2, meaning the second ring. And we go back to an s orbital because they always start, each number starts with s and then p. But the first energy level only has s. The second one has, you get 2s, 2p, 3s, 3p. You get it. There's s and p in all of them except for the first one. So that is beryllium's electronic structure, and it's not incomplete, it's complete, because if I was drawing that out as boxes, the s orbital, the s subshell can only hold 2. Nice, yeah, calcium, really long. You've put the correct answer. So it's not calcium either, because if we look at calcium, I'm not going to draw them all out. Karam's put the answer there, so you can look on the chat for Karam's answer for calcium. Calcium is 4s2, and so it's completely filled. Its final subshell is filled. Bit long. Let's go to and see where germanium is in the periodic table, right? Because I want to do shorthand here. Let me show you how to do shorthand. I already did this earlier in the video. You actually can do shorthand as well. So germanium has 32 electrons. Instead of us writing that all out, that's crazy. We'd have to write 1s2, 2s2, 2p6. Long, right? We can follow it back to the closest but noble gas, which is argon, and take that as 18 electrons. Argon has 18 electrons, and we can actually write this. So for germanium, we can write the shorthand notation, which is to write Ar, and that counts as the first 18 electrons. We just say argon is the first 18. And argon, I'm just going to put over here, argon's electronic configuration is going to be like this. I wouldn't normally do this, but just to show you, I already did this earlier, but argon's is 1s2, 2s2. Remember, the second ring, just like in GCSE, can hold 8, but we just say that 2 of the electrons are in an S and 6 are in a P. The third energy level, you get 2 in an S and 6 in a P. And that's the first 18 electrons. 10, that's the first 18. So I don't have to write that out if I do the shorthand method like this. But then I have to go 4s2. What's 32? Now this is sounding complicated, this one. 32 minus 18. You're saying why? Oh, hold on. Let me just check your question, Zainab. It's a good question. Why is there 2s but 1p? Do you mean why is there like, why does it go 1s, 2s, 2p? So coming back here, the first ring contains an s orbital. The first 2 electrons are whizzing around in a circle, in a sphere actually, more like a football with the nucleus in the middle. They're whizzing around like this. And so we just say, that remember from GCSE, the first shell can only hold 2 electrons. Those are found in an s orbital. In the second ring, over here, the second ring, the first two, remember there's 8 in the second. Do you remember in GCSE it goes 2, 8, it goes 2 in the first shell, 8 in the others. So, but that's not true at A level. It's still 2, 8, but then it changes after that. So we're going 2 in the first ring. The first 2 of the 8 in the second ring are also in an S, in a circle, like this. But then the next 6 electrons in that second ring are in something called a p subshell. Okay, and that p subshell is shaped. You don't need to know the shape if you're doing AQA, but it's just another energy level, slightly higher. They're slightly further from the nucleus, and there's up to 6 can go in there. Obviously, if you're nitrogen, you've only got 7 electrons, so you would have 1s2, 2s2, 2p3. The third energy level over here in green, I'm drawing here, the third ring from the nucleus has 1s, 3p, and then 3d. So with each ring, a new letter appears. So the first ring just has the S subshell. The second ring has the S subshell and a P subshell. The third ring has an S subshell, a P subshell, and a D subshell. Guess what? The fourth ring over here, which my fat face is in the way, but the fourth ring has a 4S, a 4P, a 4D, and a 4F. So with each new ring or energy level, as they're known, there is an extra subshell represented by a letter. And all of the S subshells can only hold 2 electrons because they only have 1 orbital. P subshells, notice there's always 3 boxes with the P's, they can hold 6 electrons, 2 in each box or orbital. And D subshells have 5 boxes. Yeah. I'll be doing a lot of sitting down through the exam period, but I'm going to get back to losing it. Is that the case with every element? Yeah. So argon, we got 4s2. Basically, you can use this argon as a shorthand when you're doing really long elements. So it's 4s2. I'll lose myself here. We need 14 extra electrons. And then, oh my gosh, we're going to get into the 3D. And there's a weird, freaky thing happens here. So just when you think, God, this is really difficult, they then throw in something weird. So you fill the 4s before the 3D. And I explained that a bit earlier in the video. Argon's going to have 2 in the 4s, 10 in the 3D, and then it goes back to 4p, which you would think would come next. And the 4p, remember we said there's 14 electrons left over. So we go 4s. It should go 4s, 4p, 4d, but it goes 4s, 3d, jumps back and fills the 3ds in. And there's 3d10, and then there's 2 left in the 4p. Now the 4p can hold 6 electrons. So this is the answer. This is the one that has an incomplete subshell. If the P subshell is complete, it would hold 6. If the S subshell is complete, it holds 2. And if the D subshell is complete, it holds 10. Yes, that's absolutely right, Karam. Yeah, it can hold 6, but it's only got 2. Or has it got 4? It might have 4. My maths is a bit wavy. So, but whatever's happened, the P subshell is not got its 6 that it needs. No probs. And then this final one, what has the electronic configuration of a noble gas? So, well, a hydrogen ion doesn't have any electrons. It's just a proton. So it's not that one. Oxygen with a minus, you might remember, I'm just going to do this last one here. Oh my gosh. Oxygen with a minus. Oxygen, you might remember oxygen has 8 electrons. So Zainab, if I have 8 electrons, what would be the electronic configuration of oxygen normally if it has 8 electrons? Normally oxygen's got 8 when it's an atom. It has 8 electrons. So we would go 1s2. First 2 electrons are in the s. How many electrons would be in the next 2 subshells, the 2s and the 2p? So Karam's got, yeah, 2 and 6, you're right. But the 6, the difference you've got to do, Zainab, is split the 6. You're absolutely right. Karam split it there. So all you do is you look, this is your old second, where you wrote 6, that's now split into 2s and 2p. So you go 2s2, it fills the s first, and there'll be 4 left, 2p4. But we have to take account, this is a minus ion. What has a negative ion done? What's happened? If you're a negative ion, what have you gained? What have you got hold of? You've gained an electron. So actually, it's going to be, right, so let me see. What if we did 1s2, 2s? Oh, you can't do 2s. I see what you're saying, Zainab. Good point. You can't do 2s4 because the s only is made of one box, one orbital. It only has enough room for 2 electrons. S's only ever can hold 2. P's can hold 6 because they are made of 3 boxes. So S's only have one little box or orbital. So we'll have to fill up the S first, and it will always go 2s2. Could be 2s1 if you were lithium with 3 electrons. You'd be 1s2, 2s1. Okay. But because this is an ion, it's gained an electron. So actually, it's 2p5. And the question was, is this a noble gas? And the answer is no. That's not a noble gas, because a noble gas would have a full energy level. So we come down. Oh, I don't want to do this one. Selenium. Where's selenium? What's selenium? I'm guessing it's selenium. Oh, I'm not doing that. Oh, well, it's going to be selenium. If I look here, okay, I'm cheating here because I can't be bothered to write the whole thing out. It's like, right, it's a long. So if we look at selenium, it's got 34 electrons. They've asked us, what's the electronic configuration of a selenium 2 minus ion, or minus 2 minus, did I write? Anyway, yeah. Selenium minus 2 has gained 2 electrons. If we jump, instead of 34, it's going to have the same electronic structure then as krypton. So I know straight away selenium has gained 2 electrons because it's a minus 2 ion, and therefore it has got the same electronic structure as krypton. So the answer for this one is actually going to be selenium. Without me draw, I could draw it all out, but I don't fancy doing that. Yeah, so these are actually some really hard. These are A-level questions. So you've got to remember, with A-level, it's very, very tricky. But whatever A-level you choose, if you're doing history, geography, whatever A-level you choose, it's going to be tough, 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 tough. So what I would say is, if you get a level 7, 8, or 9 in maths, your math skills are good enough for you to do A-level chem. If you get a level 6 in maths, you're probably going to struggle because well, when I say struggle, it depends what you're aiming for. So like, not everyone's the same. So if you're like, look, realistically, I'm only going to get a C, like I need a C, and you should use this to inform what you're going for, like when you apply for courses and things. But if you get a level 6 in maths, 20% of A level chemistry is maths, is just pure maths calculations. And they're going to be higher GCSE maths. So the 20% are going to be 20% of your A level is higher GCSE. So Zainab, if you get a level 6, let's say in maths, you can still do chemistry A level, but you would struggle. I'm guessing it would be difficult to get an A or A star with a level 6 in maths. It's not impossible. Only 20% of it is maths. But the maths is going to be higher maths. So it's going to be like it'll be the same as doing a level 7 maths question. There won't be many level 9 maths questions at all from GCSE. If you do physics, physics goes with A level maths. Some of the maths in physics, it's probably like level 9 GCSE maths or GCSE further maths is the level of the physics maths. So I would say personally, when I did my studies, I got a equivalent of a level 6 in maths GCSE, and I'm fine with the chemistry maths. Always, but obviously I've been doing it for like 25 years, so easy peasy, right? But like, it's not that hard. It's just rearranging equations. Most of the maths in chemistry A level is rearranging equations. You have to know how to rearrange an equation. Some of the equations are difficult. So, yeah. For this one, by the way, which of the following is the electronic configuration of an element with a maximum oxidation state of +5? You might say to yourself, what the hell's +5? What's oxidation state? When you form an ion, which one can, in theory, form a +5 ion? Yeah, in theory, which one has 5 electrons in the outer shell that it can lose and therefore form a +5 ion? Yeah, you're absolutement, yeah, right. And you might be sitting there going, how the hell has he worked that out? Well, let's check out A. A has how many electrons in the second ring? If we were doing old GCSE money, this one has got 2 rings. So in old GCSE, this element X, whatever we want to call it, has got 7 electrons, because look, there's a 5 and a 2. 2s and 2p just gives you a bit more information, but there's 7 electrons. That's actually fluorine in the periodic table. So that's not going to form a +5 ion. You'd have to lose 5 electrons. Then if we look at this one has got 3 electrons. This one could form a +3. It's got 3 in the third ring. And then if we look at C, if you're wondering how Karam is a genius, well, he's just looked at that and seen that the 3s has 2 and the 3p has 3. The total number of electrons in the third ring is 5. So they've just made it so it can lose 5 electrons and become +5. So they've just made it slightly more complicated. But as I say, whatever A level you choose, it's going to be tough. So now, I'm not saying like, so you could get an A in chemistry with a level 6 in maths. I'm just saying you might 20% of it's going to be kind of level 7 maths paper. So if you think of level 7 questions on your higher maths paper, there's like 20% of your A level is going to be those kind of questions. So if you're a level 7, 8, 9 in maths, you're just going to be like, oh, the maths in chemistry is easy peasy. If you're a level 8 or 9 in maths GCSE, you're just going to be like, the maths is no sweat, man. So yeah. Actually, I find the maths in the biology harder. The maths in the biology is mental maths, and I find the maths in the biology harder. It doesn't really have patterns. The maths in the biology is mental maths, and dividing, timesing really big numbers, loads of conversions. So they'll do a 2-mark question where you've got loads and loads of conversions, and you've got to work out the area of a cylinder, and you've got to work out how many bacteria, how many billions of bacteria are in 1 centimeter cubed. You've got to work out the volume of the cylinder, and then they'll say they diluted it, and then da 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 da. And so you've got to do like tons and tons of maths to come to the answer. But there's no real major math skills like rearranging equations, but it's all conversions and using big numbers and kind of, if you're good at mental maths, logically thinking, oh, that's 1,000 times bigger than that, and then you'll be great with the bio. Anyway, have a watch of this video. I go through all how to do the electronic structure. If you missed the start, then you might be a bit baffed. I think the first 5 minutes I'm talking in complete silence, so I'll have to go back over and go through that because I don't think my mic was on, and I'm like, but there we go. All right, guys. Yeah, density is mass over volume, so you're going to use a lot of that sort of stuff in biology and that, yeah, and that. In chemistry, you're not. Chemistry is more rearranging mathematical equations. So is the maths mainly in chemistry. All right, guys, take care. I'm doing biology tomorrow. Those of you that are taking bio, I'm doing biology tomorrow. So yeah, like, share, subscribe. Tell your friends who are taking biology and that. So nice one, guys. Take care. Well done, guys. And yeah, you can always download the videos, watch them later, or etc., or save them and watch them later. It will be up for rewatching. I don't know how long it takes. It takes maybe an hour after the lesson, and then YouTube just saved them on there. All right, guys. Nice one. Bye bye. Okay, I'm going.